Thanks, Subha. Thanks to the organizers for having me. Feel free to interrupt me if like my slides are not visible or if you have questions or anything. Right. So I'm going to talk about symmetry and quantum query to communication simulation. This is based on joint work with Saurav, Arkadev, Peter, Manasvi, and Ronald. It's also available on arXiv, the paper. You can feel free to check it out. So here's the outline of what I'm going to talk about. First, I'll introduce the models that we're interested in. More specifically, the quantum query model and the quantum communication model. And then I'll talk about how a problem in the query world naturally gives rise to a problem in the communication world and what bounds are known. I'll talk about some prior results, and that will set the backdrop for me to be able to state our main theorems. Think of our main theorems as two types. One is sort of an upper bound theorem and one is sort of a lower bound theorem. So if you're only interested in one of them, if you zone out of one of these sections, 3 or 4, these are sort of independent of each other. And in the end, I'll summarize. Great. So let me talk about the models of interest. So the first model is the query model. And in the classical world, this is equivalent to the decision tree model. So here you're given a known function f on n input bits. So throughout this talk, I'll be referring to bits as -1, 1 valued. So think of -1 as logical true and 1 as logical false, if you may. It's just slightly more convenient than dealing with the 0, 1 world for this talk. So you have a known function f on n input bits, and there's an unknown input x, and the goal is to compute f of x. And what are you allowed to do? You're allowed to make queries of the form, what is the value of xi? Right. So for example, this model is captured by a decision tree. So here in this figure, I've drawn a decision tree that computes a function on 5 input bits. And the way it computes a function is the following. It first asks, is the first input bit -1? If so, go down to the right subtree and proceed iteratively. And when you hit a leaf, output the value at that leaf. Okay. So this decision tree naturally computes a Boolean function f that's defined here. Fx equal to -1 if and only if x reaches a -1 leaf in this decision tree. And the cost of this tree is the maximum number of queries. So each node, you can think of it as a query. So it's the maximum number of queries you have to perform over all inputs. And this is the same as the depth of the tree. And in the randomized world, you're also allowed additional access to random coin flips. Alternatively, it's a distribution over deterministic decision trees. And these random coin flip nodes are not charged in the depth at all. So the only cost is for the queries. So what is the correctness requirement? Let me tell you about that. First of all, the decision tree complexity or the query complexity of f is the smallest depth of a deterministic decision tree that computes f. And there's a natural randomized generalization for this, which is the smallest depth of a randomized decision tree computing f. So in particular, when I say a randomized decision tree computes f, I mean the probability that t of x equals the function's value f of x for all inputs x has to be at least 2/3. So this. And now there's a natural quantum analog of the decision tree or query model. Unfortunately, it's not cleanly capturable in the decision tree setting, but it's a natural generalization nevertheless. So instead of queries of the form, what is the value of xi? You're allowed to make queries that are basically a superposition of what is the value of xi. Right? So you're allowed to query. So these are the form. This is the quantum quantization of this model, basically. Right? So you can, yeah. So a quantum query algorithm is basically a sequence of unitaries applied to a start state ket of psi naught. And in the end, you measure a designated output qubit, and depending on what you observe, you output either -1 or 1. Right? And here, These OXs are these oracle queries, which correspond to one quantum query each. And UIs are independent of the input. And the cost in this model, we ignore, so we don't charge anything for the input independent unitaries. The only charge is for the oracle queries. So this is, and again, the correctness requirement here is that the probability that the correct answer is output needs to be at least 2/3 for all inputs X. The quantum query complexity is simply the minimum cost of a quantum query algorithm that computes F, computing in this sense here. Right. So that's the query model. I hope, I expect most of you would have already seen this. Next, let me tell you about the communication model that we're interested in. Now, in this model, there are two parties, let's say Alice and Bob. There's a known function f on 2 n input bits. And the input to this function is split between Alice and Bob. So Alice has an n-bit string x. She doesn't know Bob's string y. Bob has an n-bit string y. He doesn't know Alice's string x. And they wish to jointly compute f of x comma y using a communication protocol. And what does the general protocol look like? It's like the following. Alice on input x sends a message m1 to Bob. Now Bob sees m1, and based on y, he replies with a message m2. And then they proceed so on until they both agree on an output. And let's say one of the parties, let's say Alice, outputs pi of xy, which is either -1 or 1. So this is a protocol pi. And the cost of this protocol is the total number of bits, or in the quantum world, qubits communicated, over the worst case input, x and y. Okay, so this is slightly important. So in this picture here, the cost for this input x and y would be the summation of the number of bits in mi overall I. So depending on which world you're working in, the deterministic, randomized, or quantum, the correctness requirements differ. So in the deterministic world, what you want is that for all inputs x, the protocol has to output the correct value. In the randomized world, let's say Alice and Bob have access to a public random string. There's no charge for accessing that. So one more thing I forgot to mention, I'm sorry here, is that Alice and Bob individually are computationally unbounded. So truly the only resource that we're interested in is the communication between them. In the randomized world, they have access to public randomness, and they wish that the correctness requirement is for all inputs xy, the probability of the protocol outputting the correct answer is at least 2/3. And the quantum world, the model we are interested in, Alice and Bob have access to an arbitrary shared entangled state for free. You can also talk about the world where they're not allowed access to an arbitrary entangled state, but we're going to be interested in the case when they are. And here the correctness requirement is just as before. The probability that the protocol computes f is at least 2/3 for all inputs xy. Okay. Are there any questions about the models? Okay, great. So now I'm going to tell you about, let's say you have a function in the query world. What's a natural way to convert it to a function in the communication world? Let's say you have a function f that's on n input bits. A natural way to convert it to a function in the communication world is take each of these input bits and replace it by a function, let's say XOR on 2 bits. Xi XOR Yi becomes what in the query case was Zi. Right? And you give all the Xi's to Alice, give all the Yi's to Bob. So for a query function f, this got converted to this function f of XOR in the communication world. And now I'm going to argue that given an efficient query algorithm for f, you can come up with an efficient communication protocol for f of XOR. So this is exactly the same decision tree that I drew in the first one of the first few slides. So let's say f's decision, you had an efficient query algorithm in the classical setting, In other words, let's say you had an efficient decision tree that computes f. And let's say at the root, that decision tree queries the first variable. So it queried what's the value of Z1. Now we're going to construct an efficient decision tree for f composed with XOR, and Alice and Bob are jointly going to simulate this in the communication world. So instead of Z1, we're going to query what is the value of X1 XOR Y1, because Z1 is exactly replaced by X1 XOR Y1. And just continue in the same way for all the leaves, all the nodes. And it's not hard to check that this is a valid decision tree for f composed with XOR. And now how are Alice and Bob going to jointly simulate this in the classical world, let's say? When you're, let's say at the root node, when you're at an arbitrary node that queries xi XOR yi, Alice can just send across her input xi to Bob. Bob can compute xi XOR yi, and both now they have jointly simulated the query that occurs at one node, and then they just know which subtree to follow and just simulate exactly what the query algorithm did. So what does this mean? When one query was used in the query setting, we're using 2 bits of communication in the communication setting. So the deterministic communication complexity, there was nothing special about XOR. So if we replaced it by AND, Alice could still said, if the communication problem in question was f composed with AND, Alice could still send x1 to Bob. Bob could compute x1 and y1 and send it to Alice, and they could simulate the whole decision tree in the same way. So the deterministic communication complexity of f composed with square, where square is, let's say, either AND2 or XOR2, is at most 2 times the query complexity of f. And a similar proof works in the randomized case as well. Now, what happens in the quantum world? Like I told you, there's no clean decision tree picture in the quantum world, but there is something known as a result of Buhrman, Cleve, and Wigderson from '98 that says that an analogous simulation still holds, but instead of that factor 2 that was there on the previous slide, you have a factor of order log n. And the reason why this comes in is intuitively, it's not because you have to simply simulate queries of the form xi. You have to simulate queries of what is a superposition of values, superposition of the indices. I mean, those are the potential queries. And since there are n indices, Alice and Bob can jointly simulate one quantum query with log n bits of communication, or 2 log n bits of communication, Alice to Bob and back. So there's inherently this log n factor that pops up here as opposed to 2 in the classical world. And there's a natural question, can this log n be avoided? Is it true that in this setting, the quantum world actually behaves like the classical world? So the first question is it possible that this log n isn't required at all? So is it true that for all Boolean functions f, this log n is avoidable and we can actually get away with a constant factor overhead? So it turns out that this is true for a specific function, the Set-Disjointness function. In fact, what I've drawn here is the set intersection function. So in this function, Alice and Bob are given n bit strings each, 2 n bit strings each. And they wish to know, is there an index I for which xi equals yi equals -1? So the result on the previous slide of Buhrman, Cleve, and Wigderson said that the communication complexity of this problem here is at most the query complexity of OR times log n. Hoyer and de Wolf reduced the overhead from log n to 2 to the log star n, which is almost constant, but not quite. And eventually, Aaronson and Ambainis got rid of the overhead altogether. So they said that the communication complexity of OR composed with AND is order quantum query complexity of OR. So it's feasible right now that for all Boolean functions, this log n overhead is avoidable. Until last year, that is, where we exhibited a Boolean function for which this log n factor overhead is necessary. However, this is a very specific function and it works only in the case when the inner gadget is XOR. And the purpose of this work, what I'm talking about today, is to get sort of a more fine-grained understanding about when is this log n overhead necessary and when is it avoidable. And let me state our main theorems here. So I'm going to define symmetric and transitive symmetric functions on the next slide. But for now, just believe me when I say that there are two very natural classes of Boolean functions. So we say that when the outer function is symmetric, then the log n factor is avoidable. So you can get just a constant factor overhead in the communication complexity of f of square when simulating a quantum query protocol for f. On the other hand, there exists a transitive symmetric function for which this log n factor overhead is necessary. Not only that, I know I haven't defined this notation, but let me try to explain what this is. Not only that, this says that even for quantum communication protocols that are allowed to err with probability arbitrarily close to half, this log n is necessary. So maybe let me spend a little more time. Let's say you were to construct a quantum communication protocol for some function. There's a trivial protocol of communication cost 0, but error probability half. Just toss a random coin and output what you see. Right? And in this model, you're just requiring the correctness to be strictly greater than half. You don't need it to be bounded away from half. So in this setting here, you need the correctness, the error probability to be at most 1/3. Here it's arbitrarily close to half, basically. So even in this model, so the error here is still 1/3. So even in this model, there exists a transitive symmetric function such that the quantum communication complexity of f composed square requires this log n overhead over the bounded error quantum query complexity of f. And let me define symmetric and transitive symmetric functions first. So a function is symmetric if it only depends on the Hamming weight of the input. By Hamming weight, I mean the number of -1s in the input. Most of the functions, a lot of the popular functions such as OR, AND, majority, parity, all of these are symmetric functions. In other words, no matter how you permute the input bits, the function value remains unchanged. There's a different view of symmetry. And there's a generalization of this, which is transitive symmetry, which I'm going to depict. I'm going to show you a figure after this. But so what this says is for all indices I and j, so a function is transitive symmetric if for all indices there is a permutation that maps I to j and such that the function value is unchanged for all inputs under this permutation. So let's look at an example. So majority by itself, so majority is the function where you output -1 if the number of -1s in the input is greater than the number of 1s. So this is a composed function, a depth 2 composed function, majority of majority. This is transitive symmetric. Why? Let's say you have an index I here, and let's say you have an index j here. I'm going to define to you a permutation such that the function value is unchanged, but I maps to j. So first thing is you just map this whole block of inputs to this whole block of inputs and do a permutation inside this block such that I maps to wherever j was before. So I hope at least roughly you see what transitive symmetry means. And now since I've defined it, I'll go back to our main theorems here. And are there any questions about this? For the statements? If this is confusing, you can just assume. So this is a stronger model than the regular quantum communication complexity model.
Maybe I have a question, Nikhil.
Yeah, Harry.
So this transitive symmetric functions, has that been defined before, or is that something that you defined to make the proof?
No, it's been defined before. There's been studies on different properties of transitive symmetric functions.
And can you say a little bit of why this was studied, or is sort of the next step up after symmetric?
I guess
to capture a little bit broader class of functions like the majority of majorities, for example.
That's true. So I don't know why it was introduced in the first place, but you're right. It's sort of it's a natural generalization of symmetry, I guess.
Good.
Yeah, I don't have a better explanation than that. I'm sorry, but yeah, it does. You're right. It captures a slightly broader class than symmetric functions. That's about it.
Thanks.
If I may add something, there's a lot of study of complexity of graph properties that have this transitive symmetric property. Like in the context of Andera Rosenberg conjecture, also in the context of sensitivity, it has been well studied. All sorts of Boolean functions with transitive symmetric property.
Yeah, isn't it what they sort of use for this evasiveness? I think it's called. But I mean, this has been a long time that I looked at that.
Well, I guess the sort of the symmetry you want for graph properties is
That's
typically
different.
halfway between these two kinds of symmetry that are on this slide.
Ah. Okay, thanks. Thanks a lot.
Can I also ask a very basic question? So sort of this transitive symmetric, it just means that it's symmetric under some subgroup of the, like any subgroup of the symmetric group that acts transitively on the set N. Is that the correct way to see it? That you just replace the action by Sn with some subgroup of Sn that still acts transitively? Or it doesn't have to be a subgroup, I guess.
I'm not sure if that's equivalent. I mean, because we need for all pairs of indices, I'll need to think about it, but there is some formulation in the setting that you mentioned, but and one important thing is for all indices, you need there to exist.
I think you're right, Freek. You study the set of permutations under which the function is invariant, and that forms a group, and you want this group to be transitive.
Yeah. Okay. Yeah. Exactly. Yeah. That makes sense. Thanks.
Yeah. Thanks, Yor. Yeah. That's right. All right. So if there are no more questions, I'll carry on. Great. So let's go back to the main theorems. So the first theorem I'll prove to you, or I'll provide a sketch of the proof, is the theorem 1 here. So basically, if you have a quantum query algorithm for a symmetric function, we're going to take an optimal quantum query algorithm for a symmetric function and sort of port it to the communication world and give a communication protocol for f composed with square without incurring this overhead. And it'll be helpful to keep the outer function as OR in mind for my sketch of the proof. All right. So first thing, we need to know what is the optimal query complexity of symmetric functions. So like I said, symmetric functions are those that only depend on the Hamming weight of the input. So this is sort of representation of a symmetric function, where these dashes, these vertical lines represent Hamming weights of the input. So mod x refers to the number of -1s in the string. And let's say this horizontal line is function value equals 1, and this horizontal line is function value equals -1. So you can plot out what happens to the function f when it's fed an input of Hamming weight I. And that's exactly what we're plotting on this line. And now there's an interval around Hamming weight n/2 where this function acts like a constant. For all we know, that interval might be empty. But just draw out that interval, call the length of the left-hand side T0, the right-hand side T1. And it turns out that the quantum query complexity of symmetric functions is theta of square root of n times the max of these two quantities. This is a result. This follows due to result of Beals, Buhrman, Cleve, Moscow, and de Wolf. Let's just take a look at an example. Let's say the function is OR. So how does its spectrum look in this case? So when the Hamming weight is 0, the value is 1. And on all other Hamming weights, it outputs -1. So in this case, T1 is equal to 0 because the interval starts here and ends here. So T1 is equal to 0, but T0 is equal to 1. So the quantum query complexity of OR is theta of square root n. Great. Okay, so now let's say you're trying to solve OR. using Grover search algorithm, or more specifically, or more generally, amplitude amplification. Right? So I want you to think in the background, there's a hidden string X, an n-bit string. And your goal is to find an index I for which xi is equal to -1. And your initial starting state is a superposition over all indices. So psi is the uniform superposition over all indices, some 1 over root n summation ket I. And its good component is basically all those indices for which xi is equal to -1. It's a uniform superposition over those indices. And it also has a bad component. And your goal is to perform a series of reflections such that your initial state psi gets mapped to a state that's close to ket G. And by close, I mean the inner product of this final state with ket G, you want it to be large. And what do you have access to? You have access to two types of reflections. A reflection around ket B, which is essentially an oracle query in the query complexity setting, and a reflection around ket psi, which is free in the query world, because it's input independent. And how do you do this? I'm sure a lot of you would have seen this at some point. You start with psi. Let's reflect around ket B. This corresponds to an oracle query of cost 1 in the query world. So the angle theta gets reflected here. Now reflect around psi again. So this angle becomes 3 theta. And now what you would do to get closer to ket G is, again, you reflect around ket B, again reflect around ket psi. So the angle 3 theta becomes 5 theta, it becomes 7 theta, and so on. You keep additively increasing by 2 theta every time. And with the correct number of iterations, whatever I mean by that, you're going to reach close to ket G. We are going to view it slightly differently in an iterative fashion. It helps in our analysis. So let's say you've performed this first iteration, you've reached an angle of 3 theta. In general, let's suppose after j minus 1 iterations, your state is now ket of psi j minus 1, and your angle is theta j minus 1. Reflect around ket B. And then it turns out that, okay, let me write this down here. So first, your initial state ket psi, you apply a j minus 1 to it. It maps psi to psi j minus 1. Then reflect around ket B. That's this step here. And it turns out that this product of reflections is, this sequence of unitaries just performs a reflection around ket of psi j minus 1. So psi j minus 1. So your angle triples basically here rather than an additive 2 theta each time. And I'm not cheating. The cost also blows up. So the cost of AJ turns out to be you're using AJ minus 1 3 times, and you're invoking an oracle query once. So the cost of AJ is just 3 times AJ minus 1 plus 1. So in this world, it turns out that if your initial string X, which is hidden in the background, if it had T indices for which Xi is equal to -1, with square root of n over T queries or square root of n over T cost, you can reach a state that's close to ket G. And that's a quantum query algorithm with asymptotically optimal query complexity for symmetric functions. Right? Now we want to port this to the communication world. So for now, you can just ignore everything until here. So let's say you're in the communication world, and now hidden in the background, there are two strings, X and Y, n bits each. And your goal is to find an index I. So this is corresponding to the set intersection problem, which is OR composed with AND on 2 bits. So Alice and Bob have two n-bit strings. Their goal is to find an index I for which Xi is equal to Yi equal to -1. And now the space in which they're working is the initial state psi, which I haven't drawn here, is a summation of ket I. Although I haven't written it, this register belongs to Alice, this register belongs to Bob. And the good component is this state is the uniform superposition over all ket I for which Xi is equal to Yi equal to -1. So these are like the solutions, and we wish to find one of these solutions. And what's a natural communication protocol for this? Alice and Bob can jointly simulate the query algorithm that was on the previous slide. So you can reflect around ket B, reflect around ket psi, and then iteratively perform the same process again and again. Now, I'll jump to the next slide. This is the goal. The issue here is that if you want to reflect around ket psi, this is no longer free in the communication setting because ket psi is the shared state between Alice and Bob. And in order to naively simulate this reflection, Alice would send across her register to Bob, which is costing log n qubits. And this is precisely where the log n overhead comes from. And our goal is to save that. And the way we're going to save that is we're going to be able to tolerate some error here with some efficient communication cost. So the key idea is the key ideas are the following. The initial state ket psi, sorry, this should be a ket, and I missed a ket on the previous slide as well. I'm sorry. Is just log n EPR pairs. And remember, in the communication setting, this is allowed for free. This is given to Alice and Bob for free in the model that we're interested in. Now I'm lying a bit here, but we can actually, this is fixable. The reflection around ket B can be implemented perfectly using 2 qubits of communication. So this is no longer an issue. But it turns out that rather than the naive protocol of log n for reflecting around ket psi, there's a result due to Aharonov, Harrow, Landau, Nagai, Segedi, and Vazirani that allows us to reflect around ket psi with log 1 over epsilon qubits of communication, but at the cost of an error of epsilon in the angle reflected. So basically, you can reflect around ket psi with constant communication if you're willing to tolerate constant error. And the rest of the analysis is basically choosing these epsilons carefully. And it turns out that the communication complexity of the resultant protocol is basically the query complexity of the protocol we started with just a constant factor overhead. So this whole argument that I gave you was sort of designed for the case where you're trying to find an index I, where Alice and Bob are trying to find an index I, for which xi equals yi equals -1. So it's the set intersection problem. So it's OR composed with AND. More generally, if you have a symmetric composed with AND, you can run the same, a similar type of argument. Just repeat this whole thing, find solutions over and over. I'm going to skip this slide, but trust me when I say that it's extendable to symmetric functions without too much of an effort. And yeah, so that gives our function again. So the whole the sketch that I gave you was designed when the inner function was AND, but it can also be edited to to work when the inner function is XOR, or more generally any function with small exact quantum communication complexity. So the quantum communication complexity of a symmetric function composed with a small gadget, or a 2-bit gadget in this case, is order quantum query complexity of f, and there's only a constant factor overhead here. So are there questions at this point?
So maybe one question. Could you also have functions where you sort of, for instance, you take like the OR of the first 2 bits and then the end of the second 2 bits and then maybe the OR again of the etc. And then compute sort of the composition of that with some function f?
I'm not sure I quite understood what your function was. So you could compute the OR of the first 2 bits and then the, oh, I see. You're saying when the inner function is not necessarily same for all.
Yeah. Because like I was thinking in the classical model, sort of that would be okay, I guess. Where like if in this classical trick where you just follow the tree, then that would be fine.
That's right. That's a good question. I think it would be okay in the the quantum model as well needs to be worked out, but I'm reasonably sure you should be able to make it work.
Can't you just apply the Morgan's law here to make like the ands into ors by simply redefining part of the function?
Well, I'm not sure if that would work. I mean, the outer function, the outer function structure would sort of change if you feed it variables and negated variables. I don't know if De Morgan's laws would work as it is.
You would maybe lose the symmetry there.
You don't need to do that. I think our method works fine when all the inner functions are different. The only thing that changes is that the 2 bits of communication, which is the cost of implementing OG, gets replaced by the maximal communication complexity among all the different occurring inner functions. They could also be on more than 2 bits. It all works fine.
Sure. So I think the key change that's going to happen is you're just going to redefine the good states in a slightly different way. And yeah, like Ronald says, I think everything's going to work out cleanly. Thanks. Any other questions?
Oh, I have a maybe silly question. So this, like you said, this is all for the symmetric properties, right? Symmetric functions. So is that because of the first theorem that you mentioned, which is like the max of root n t1 or t0 something? Because there is a query like upper bound for every symmetric function.
Yeah, so we know that this is tight. Okay. And we in fact know a query algorithm for this. So what we did is we took that query algorithm that solves the symmetric function and converted it to a communication protocol without any overhead. So it was crucial that we know a quantum query bound here for symmetric functions. You're right.
Okay, thank you.
I'm not sure if that answers your question.
Yeah, it does. It does.
Great, thanks. So let me carry on. And now the second part of the talk is we're going to say that there exists a transitive symmetric function for which the log n overhead is required over here, even in a stronger communication complexity model. So there's 3 parts to understanding this part of the talk. The second part is going to be understanding the upper bound. Third part is going to be understanding the lower bound. And the first part, and in my opinion, the hardest part, is going to be understanding the function we construct. So I'm going to spend the next few slides trying to give you ideas about, or try to make you understand what our transitive function is. By transitive, I mean transitive symmetric. I might use it interchangeably. So we're going to show an upper bound on the quantum query complexity of order m. In fact, it's going to be theta m. And the lower bound is going to be omega m log m. And notice because of this omega here, this is the same as asymptotically the same as omega m log input size, which is 2m square here. The function construction is inspired by this previous result of ours, which in turn was heavily inspired.
To interrupt you, Nikhil, but the QCC lower bound, this is for the unbounded error setting, right?
That's true. So yeah, although I've stated it here in this form, it is true, but this lower bound holds even when the error is arbitrarily close to half. So which is the unbounded error model, like Ronald pointed out. Yep. Yeah, so the function query and query upper bound is inspired from a previous result of ours, which in turn was heavily inspired by a result of by a function construction and query upper bound of Ambainis and de Wulf in 2014. The lower bound is simply fixing variables. So Alice and Bob, suppose they wish, sorry, it's simply fixing variables to an input of inner product m log m. Yeah, so the lower bound is going to follow a reduction. So it's known that the communication complexity of inner product m log m is maximal essentially, even when the error probability is arbitrarily close to half. So the unbounded error communication complexity of inner product m log m is maximal. And Alice and Bob are going to use a reduction, a local reduction, to convert an input to inner product m log m to f composed with square for any square in AND 2 or XOR 2. Okay, so now let's get to the construction of the function. It's like a composed function. It's not quite a composed function. I'll explain why. So the outer function is a parity on m input bits. And the inner functions are HIP. HIP denotes Hadamardized IP, I guess. And I'll define what that means soon enough. So to understand HIP, we need to understand what the inner product mod 2 function is, which is exactly the following. It's a parity composed with a bitwise AND. So in the 0-1 world, this would exactly be summation of xi yi mod 2. And the -1 world, -1 world, or more generally, it's parity composed with AND. Good. And now I just have to define to you what a Hadamardization of inner product is. So for that, let's see what Hadamard code words are. So for a log t bit string, a Hadamard code word corresponding to I is the t bit string that enlists all of its parities. So for example, let's take log t equals 2 and t equals 4. So log is base 2. Suppose you have this 2-bit string here. So parities are just products of subsets of variables. So what's the empty parity? It's just 1. The empty parity is always 1. So what is this variable? It's a 1. Then the second variable is a -1. And the product of the first and second variables are -1. So the Hadamard code word corresponding to this 2-bit string I is the 4-bit string 1, 1, -1, -1. Therefore, out of the 2 to the t many possible t-bit strings, exactly t of them are going to be Hadamard code words, valid Hadamard code words. Now I can define our inner function, HIP, a Hadamardization of IP. So the way it acts is the following. First check, so it acts on 2 m input bits. Check whether the first m input bits are a valid Hadamard code word of a log m bit string. Check whether the second m bits are a valid Hadamard code word of a log m bit string. If they are, then output inner product of a comma b. So it's an inner product of 2 times log m many variables if both of these blocks are legitimate Hadamard code words. Else output a special symbol phi. So this is a partial function. In fact, it's heavily partial. I mean, most of the time it's going to output phi. And a crucial thing we're going to use is the following form of the Bernstein-Vazirani algorithm. If you have an m-bit string that is a Hadamard code word, then the Bernstein-Vazirani algorithm uses one quantum query and recovers the string A of which it is a Hadamard code word. Good. So I can finally define our final function, which is a parity composed with Hadamardized IPs. Now remember, I said these Hadamardized IPs can output phi, so they're partial functions. So the way we're going to complete this function is the following. If any of the inputs to parity is a phi, output -1. Else, output the parity. So again, let's stare at this function for a little bit longer. Let me again tell you what the function is. So each of these blocks acts as the following. First, check whether this is a valid Hadamard code word. Check whether this is a valid Hadamard code word. Suppose they are. Suppose they are the code words of A and B. Then output the inner product of A and B here. And you do the same thing on each block. So in the case where all the blocks are Hadamard code words, it's going to be parity of inner products, each of those inner products on 2 log m bit strings. So there's a quantum query algorithm, which is going to use 2 phases. First is a guess phase, where we're going to guess whether each of the blocks are legitimate Hadamard code words or not. And this is going to use the Bernstein-Vazirani algorithm, 1 for each block. The next phase is going to be a check phase, where we're going to check for whether the output of this the guess phase is actually correct. And it turns out that this boils down to just looking at equality of two m² bit strings. And this can be done using Grover search. And if the check phase succeeds, so if the check phase tells you that yes, all of the blocks were indeed Hadamard codewords, then output the parity of the inner products of each of the blocks of the relevant variables, else minus one. So let me skip the correctness, but it's fairly short, as you can see, and I'm not hiding anything in the correctness here. And the query complexity of this algorithm is going to be 2 queries for each block. So 1 query for each m-bit string in the input. So the total number of queries used by the guess phase is 2m. Grover search is an equality check over 2 m² bit strings. This 2 is not really necessary here, but it's a square root of order of square root m². So the total quantum query complexity is just order of m. And since the outer function is a parity, you can also argue that the query complexity of this function is omega m. Right, and now for the communication lower bound, suppose Alice and Bob are given inputs. Suppose their goal is to solve inner product m log m. I want to argue that given a protocol for f, or f here, given a protocol for f composed with square, so let's say square is and for convenience, what does that mean? That means each variable here is a bitwise and of 2 bits, one with Alice, one with Bob. So I want to argue that given a protocol for f composed with square, we can extract a protocol for inner product m log m. And how are we going to do that? Alice and Bob are going to take an input to inner product m log m and convert it to an input for capital F composed with square. Yeah, I won't spend too much time on how the conversion works, but at a very high level, Alice and Bob have inputs to inner product m log m. They break it up into chunks of size log m each. So they have inputs to, let's say, inner product log m, and so on. So m many chunks. And the final output of their function is supposed to be parity of these inner products, because inner product is exactly parity of inner products. So they convert each of these log m chunks to a valid input to one of the Hadamardized IPs. Basically, that's the very high level idea of what happens here. So essentially, Alice and Bob can convert an input, like I said, xy to inner product m log m to an input for f of square. And it turns out that this reduction is legitimate in the sense that inner product of small x, small y is -1, if and only if capital F of square of x comma y is -1. So what does that mean? That just means that the communication complexity of F composed square under whatever model you consider is at least the communication complexity of inner product m log m, since this reduction was completely local. And Forster's theorem says that even in the unbounded error model, the communication complexity of inner product m log m is omega m log m. Now there's one thing I haven't told you. This function f, capital F, is transitive. There's a fairly straightforward proof by staring. If you understand the function well enough, you'll realize at some point that it's transitive. So I'm not going to prove that here. So here's a summary of what I spoke about. So the theorem 1 was said that when your outer function f is symmetric, the quantum communication complexity of f composed square is order q of f. So this log n overhead is completely avoidable in that case. Theorem 2 said there exists a transitive symmetric function for which this log n overhead is necessary, even when the communication model is the unbounded error model. So we have some other results in the paper. So there's a generic recipe to construct functions for which you require this log n overhead. And then we also recover our earlier result using a more general technique. And I mentioned that our earlier result had only worked when the inner function is XOR. We can also recover that when the inner function is AND using this technique. And finally, one open question that's left is our communication upper bound here assumes shared entanglement. So it turns out that it assumes order T log n shared EPR pairs. Let me try to just quickly remind you what T was. I glossed over it. So you have a symmetric function f that defines a predicate on how f acts on Hamming weights I. So it's a univariate function now. You plot out the interval around n by 2, the largest such interval where f is a constant. And the maximum of the remaining length on the left or right is T. So it turns out that our quantum query upper bound here, quantum communication complexity upper bound, uses order T log n shared EPR pairs between Alice and Bob. Since we were interested in the model where shared entanglement is free, this didn't affect our communication complexity. But it turns out that if T is not very large, this can also be absorbed into our communication protocol by Alice and Bob spending this much communication to establish the pairs in the beginning of the protocol. But this doesn't fail. So for example, when T log n dominates the quantum query complexity of F, this doesn't work anymore if you don't allow shared entanglement here. So can one avoid this? That's, I guess, an concrete open question that comes out of it. And that's it. Thank you.